So in the previous experiment, what we saw is the response of the system to step input or pulse input, RC first order system, as well as second order system, RLC and RL, and so we gave pulse input and we saw the response. So that is called zero state response, because the output is entirely due to the input applied. Another kind of response that we have come across is basically called zero input response. So the total response is basically the sum of zero state response and zero input response. So what I would like to do today or demonstrate today is that all the circuit that we have considered earlier, we can also look at the zero input response. So let us start with building that circuit. Let's say start with a RC circuit. So we take a we don't need a voltage source, so let's start with just a capacitor, and then we have a resistor, okay, yeah, so these two components, and then we have a ground. So we are not applying any voltage source, and then we connect this circuit. Okay, so there is no voltage source here, and we give a reference because the software require some kind of reference. And let's give some values for this, let's say 1 ohm, and then let's say 1 micro, some values I gave. Maybe I'll increase this resistance to say 1 kilo. These are typical values. 1 kilo resistance and 1 micro capacitor is very commonly available in the lab. So we will use those values, whereas 1 ohm is not practically we don't use those 1 ohm or any capacitance like 1 farad or 1 millifarad we don't use in the lab. But 1 micro, 1 nano, these are the kind of values that we use. So now you see the product RC, which is determining the characteristics of the circuit. The time constant, it is equal to 1 millisecond, right? It is basically the product of 1K and 1 microfarad, so that will come around as 1 millisecond. So 1 millisecond is the time scale that will the scale of time which determines the change of the voltages and currents in the circuit. Okay, they will be changing in the order of RC, the product of R and C, time constant. Now, so if there is no input, waveform, if you look at, if you measure the, if you run this, say, let's say we are applying a transient analysis. Let's say since the time constant is 1 millisecond, let's say 5 millisecond, if you take the time, we will execute the simulation for 5 millisecond, and then the time step, that is what should be the minimum interval on which the voltages and current should be evaluated. That if you specify like say 5 micro, okay, so that you will get around 1000 points in 5 millisecond. So if you give this, then if you evaluate the current, you see that it is the voltage is exactly 0 and the current is also 0. So there is nothing interesting here. Okay, so this is a case where we don't have any input, we don't have any initial conditions also. So it's zero initial conditions and zero input, the circuit will not respond. So earlier what we saw is we had a voltage source which was a pulse waveform, and the circuit responded to that. Now what we are going to introduce is basically is an initial condition. So to give initial condition, you can give a spice directive by clicking on dot of P, and then you can mention a command .ic for it's a shorthand notation in spice language. Spice is a language which is used to model devices and components and circuits, how they are connected, what are their initial conditions, etc. So I would like to give a initial condition. I would like to specify the voltage on the capacitor. Okay, so the voltage on the capacitor I would like to specify. So I would like to call the node voltage of the capacitor as Vp. I am yet to define what is P. So let's say that I have a initial voltage equal to 1 volt. Okay, I have an initial voltage equal to 1 volt. So I am specifying that at point P I have a initial voltage equal to initial condition. Okay, I am specifying some voltage. Initial condition could be either current or voltage. So that is the time t equal to 0 instant we are specifying. At point P we have a voltage. Now I have not specified what is P, so let me just specify that. Take a label and put it as the voltage across the capacitor, because one other side is grounded, so it is the voltage on the capacitor. When I specify the voltage at point P at time t equal to 0, I am specifying what is the initial voltage on the capacitor. So there is some charge initially on the capacitor at time t equal to 0, and because of those that non-zero voltage, non-zero initial condition, I will have some current flowing in the circuit. So this is what we call as zero input response. What we saw in the previous two experiments, they are zero state response. We assumed all initial conditions as zero. We did not introduce any of this. But right now we are saying there is a non-zero initial condition, and we don't have any voltage applied externally. So what is the response? Now if I run this simulation, and look at what happens to the voltage, so you see that I get a voltage which is exponentially decaying from 1 volt, which was my initial voltage. So I specified there is a non-zero initial condition which was 1 volt. I could specify -1, +1, +2, whatever I want. So that is a voltage I am assuming to be present across the voltage, because there is a charge stored in the capacitor, and at time t is equal to 0 we have this voltage, and then with respect to the time how that voltage is going to change. Okay, that is the simulation. So this is basically the zero input response, because we are not given any input, but we are getting some output, some response. So you see that it decays. And as I told you, the time constant is basically RC. RC is 1 millisecond. So this is 1 millisecond, from 0 to 1 millisecond. That is one time constant. And if you look at the expression for this decay, you can evaluate this by using Laplace transform method, which I taught you in signals and system. You can evaluate this the response of the circuit. So since input is 0, the Laplace transform of the input, you write it as 0. There will be only one term which is due to the initial conditions, which is basically V of 0 minus, okay, Vc of 0 minus. So that will have some response like this. And time constant is defined as the value it takes to reach when time reaches one time constant, we have the output changing from initial value to 1 by E. 1 by e. E is basically the natural logarithm base. So 1 by e, whatever is 1 by e, so that will be the value. So you can go to your cursor, you take a cursor, if you want to measure it, you shift it into the 1 millisecond point, and then you can see that the vertical value is 3666, okay, 366 millivolt, or 0.36 millivolt. Okay, now that is the value for 1 by e. Okay, 1 by e of the initial value, which is 1 volt. Okay, so that is how the definition of the time constant is made. Okay, I think I taught this already, so I don't want to repeat the mathematics again. So you can work it out and see this. Okay, is there any doubt with respect to this simulation? You can ask. Now if I change this to, say, instead of 1, if I say -1, then what will happen? Let's see. So if I change to -1, from -1 it gradually exponentially rise and go to 0 volt. So basically it try to achieve a steady state value, and the steady state value is basically 0 volt voltage across the capacitor. So whatever charge that was stored in the capacitor, it will be discharging. If it is a positive charge, it will reduce and reduce and go to 0. If it is a negative charge, it will increase and increase and increase until it becomes 0. So finally there will be no charge stored on the capacitor, so that is a steady state. That means at a time much larger, that means when time goes to infinity, the voltage on the capacitor will become 0. Okay, so because the charge will not be there. Any questions on this simulation? I give you a short time for asking question, otherwise I will move to the next circuit. Okay, assume that you are okay with it. This is EXP experiment. This is number 5. Okay, A. So this week I will put up a link for you to upload your reports. Alright, so now let's go to the next experiment. So next one I want to do a RL circuit. So again, I don't want any voltage source here. I will take a resistance. Okay, I have a resistance, and then I will take an inductor. So only these two components I want to have. Then I need a reference, because LT-Spice need a reference point to measure the voltages, and then I'm connecting it again. I have no excitation for this circuit. There is no external excitation, no source, no voltage source, no current source, nothing. And again I'm going to give some values which are practically available. So the value, say 1K again, and this one I will give, say, 1 millihenry. Okay, so we have this 1 kilo resistance, 1 milli. So the time constant depends upon L and R. So so what was the value of the time constant that we studied earlier? Was it time constant increases with inductance, and decreases with resistance. So it is 1 milli by 1 k. Okay, in RL circuit it is L by R, right? That is the time constant in RL circuit, L by R. So L by R, if you find out 1 milli divided by 1 k, that is 1 micro. Okay, so for this circuit the time constant is going to be 1 micro. So that is the time scale in which we have to run the simulation. So let me run it for 5 micro, and then again I am saying that it should be 5 nano, so that I will get 1000 samples in the limit I am simulating. And again, so let me find the current, it is 0, find the voltage, 0, everything is 0. There is no response because the circuit has no excitation, no external voltage source, current source, nothing, and the initial conditions are all 0. So now what I'm going to do is that I'm going to add a spice directive in order to specify my initial conditions. So dot IC, this time I'm going to specify the current through the inductor. I'm going to say that initially there was some current flowing through the inductor at the start of the simulation. There was an initial condition which was not 0, and let's say that current is flowing downward, and its value, let's say that it's equal to you can give any value, but let's say 1 milliampere. Okay, so 1 milliampere current is flowing at time t equal to 0. So whatever we say with dot IC, we are specifying for time t equal to 0. That is what we call as initial condition. Okay, the simulation is starting from initial value of time, which is 0, and it continues to 5 micro. Okay, but at the starting we say that there is some current flowing through this circuit already, and let's see how that current changes from t equal to 0 to higher time. How does it change? So let us simulate now. So we are looking at the current. It was 1 milliampere. Okay, yes, it is 1 milliampere. Again, you see that in one time constant, that is 1 microsecond now, the ratio of L and R. Okay, L by R is called the time constant. The initial value of current reduces to 1 by E, and 1 by E is basically, E is something like 2.7. so if you take 1 divided by 2.72, so you will get 0.367. Okay, so that we have seen earlier also. It is the same here also. Only difference is that for the given resistance and inductance value, the time constant is 1 microsecond rather than 1 millisecond. So that's why we are plotting the x-axis up to 5 microseconds, some 5 time constant, so that we see the waveform in a pretty neat manner. All the important parts are able to be observed properly. If you plot it to say 50 microsecond, then we won't be able to see the details. Okay, we will only see a sudden discharge, and then it goes to 0, and then everywhere it is 0. And on the other hand, if I reduce it to say 1 microsecond, then I will be only see a portion of this wave. So it is advisable to plot things to a extent of 5 time constants. Okay, for the given circuit there is a time constant involved if it is a first order circuit, and then you plot the waveforms, current or voltage, up to that amount of time. And now if I plot the voltage, as you can see that the voltage goes to voltage is the blue diagram, and it goes to 0. Initially the voltage is -1 volt Okay, I have not specified this, I only specified the current, but then the simulator calculates for 1 milliampere current to flow from top to bottom, what should be the voltage that should be coming across the inductor. Okay, so there is a relationship between inductor voltage and inductor current, so that it calculates and then it find out. Okay, because the current cannot remain the same, it has to go to 0, so there is going to be a rate of change of current, which is basically the slope. So this slope, as you can see, it is negative, it is going to decrease, the current is going to decrease, and therefore the voltage has to be negative. Okay, and as the slope reduces, the voltage reduces to 0. So voltage is basically the slope of the current waveform in inductor. We know the voltage across the inductor as L di by dt. Okay, so that's what you are seeing here. And then if you want the voltage across the the resistance, then you can measure that also. So what you have to do is take your pointer and then so which is basically same, because I don't have any other component here, so the voltage on the inductor is same as the voltage on the resistance. There is no difference because we are measuring it with respect to the ground, so they both have same, they are basically in parallel, the resistance and inductor are both in parallel, and therefore the voltage across them are the same. Okay, only difference is that if I want the voltage on the left point with respect to the right point, then I need to take a negative of the node voltage VN001. That's all. That's the only difference. Otherwise the left point is ground point. Alright, so any question on this simulation? Okay, there is no question, we'll go forward. This is experiment 5B. RL 0 input response. Okay. Next we are going to do the second order system, which we saw in the previous experiment. So we need different components, so let's take them one by one. So we have resistance, then we require an inductor R, then L, then I can have a capacitor. Okay, now I'm going to specify the value of this one as 10 ohm, and this one as say 1 milli, and then okay, so these are the values that we have taken earlier, so I'm putting it same 1 milli here also. I mean, these values are not really practical values in the lab, but since I have used them in the earlier simulation, I'm putting the same values here. Then I need a ground. So again, I'm not having any voltage source here also. Absolutely no voltage source. So I just connected this. So if I now do a simulation on this transient analysis, I should not get any waveform. No decaying current, voltage, nothing. Okay, so let's check that. Run. So what should be the time scale I should consider here? So here Since it's a second order system is characterized by two parameters. One is basically the undamped natural frequency, which is 1 by root LC, and which I think earlier we evaluated. 1 by root LC is omega, and omega is basically, if you take it will come around 1 kilo, 1 by root LC omega, and then if I divide it by 6.28, it is something like 159, right? So that is the frequency, and 159 hertz. Now 159, if I take the inverse, I get a sense of the time period involved. So 159 inverse, or let's say 1 divided by 159, so that's like 6 milliseconds. So that is like one period of the undamped natural frequency that we observed earlier, 6 milliseconds. Now if I want to plot some few cycles of those, then maybe 30 milliseconds is a good idea. So I am going to give the simulation for 30 milliseconds, and time step, let's say I'll put 1000 points, so 30 micro. So whatever is the early value I give 1,000th of that, so that I will have 1000 points for the simulation. Okay, so now let me plot the voltages and current. So for 0 to 30 millisecond, it is plotting the voltage across the capacitor is 0, current through the inductor is also 0. That is what we expected, because we have not given any initial conditions, or we have not given any input voltage source or current source. Okay, so now let's give the initial conditions. Now initial conditions I can give either the capacitor voltage, so initial dot IC. So I need to, let me specify before I give initial conditions okay, or I will specify a little later. So voltage at point say B is equal to 1 volt. So I have not specified what is B, so let me now specify what is I will specify 2 points. One is A, and that is this point, and then let me specify the point B. So point B is this point, the capacitor voltage. Okay, so what I specified is the capacitor voltage is 1 volt, and I know one thing, that it should go to 0, okay, because the capacitor, if there is some voltage, then it has to discharge and go to 0. But how it goes to 0 is what I want to observe as the transient response in this particular circuit. Okay, so from time t equal to 0, initially the capacitor voltage is 1 volt, and then we know that it goes to 0, but how does it go to 0? So let us see how that happens. So you see that from 1 volt it decays and goes to 0. Okay, so it goes gradually, slowly, it goes to 0. Now this is a second order circuit. So for second order circuit, we have other things which we can do. That is, we can control the power dissipation. So the power dissipation can be reduced. If I say instead of 10 ohm I give 1 ohm, let's see if I reduce the resistance value, then can it go like before, or will there be any change that will be coming in? So let's see what happens. So again I am plotting the voltage on the capacitor. So now you see that something very interesting is happening. It is going to 0, but instead of remaining at 0, it has gone to the negative voltage. That means whatever charge that was stored on the capacitor, it was discharging, but then it charged the capacitor in with a negative voltage, which means that earlier the top plate was positive and the bottom plate was negative. Now if you look at you see that the bottom plate become positive and the top plate become negative. So that is why we have a negative minus 0.3 volt. So that has happened, and then from there again ultimately it has to go to 0. So it tries to discharge again, and then it little bit overshoot is there, it goes beyond 0 volt, and then again it comes back. So with minimum 1-2 oscillations it has gone to 0. Okay, so with the reduction of the resistance some interesting thing is happening. So we don't have much loss, so let me further reduce and make it 0.1. This is for study academic purpose. Usually practically if you are doing it, maybe you should not put any series resistance, just capacitor and inductor in series, because the ideal practical inductors will have some small resistance, so that is enough to get some 0.1 ohm. So now let's see what happens. So I expect this oscillation to increase and become more dominant. Yes, so you see that with 0.1 ohm no much power is dissipated in one cycle. Okay, it has got sufficiently large amplitude, and there is so if R is 0, I will get undamped oscillation, which is what we studied earlier. But if R is not 0 but something small, then there is a gradual decrease. Okay, the oscillation of the amplitude of oscillation gradually decrease and then go to 0. So you see that initial amplitude is something like 8 volt. Okay, although we had applied only 1 volt, but then to have that 1 volt across it begins to discharge, and then it goes to minus 8 or minus 9 volt, and then 8, but gradually decreases and goes down to 0. So you can have like control of this oscillation or the by increasing or decreasing the resistance. So the resistance is what determines whether there will be oscillations or not, and you can derive what should be the value of resistance, like earlier we have studied, which is required for oscillation and no oscillation. So I think I discussed it already. So it is the same theory, but only thing is that now we are looking at non-zero initial conditions. This is one way we can give initial conditions. Okay, so from 1 volt, then minus 1.2 volt, then few oscillations, 1 or 2 or 3 or 4 oscillations, and then it goes to 0. So this is one way I can give the initial conditions. The second way I can give initial condition is that I can give instead of the voltage, I can give the current in the inductor. So current in the inductor and voltage on the capacitor, these are basically the normal initial conditions in a network. Okay, so now I am saying that it's a very huge current. Let me reduce the value to say 1 milli. So let's say 1 millisecond or 1 milliampere is the current that was flowing initially. So okay, even 1 milliampere is also very huge in this particular circuit. Okay, so you see that it has gone to very humongous value of current. If at time t equal to 0, suddenly if you have this amount of initial conditions, then after few oscillations it die out and go to 0, and you can plot the voltage on the capacitor. Voltage on the capacitor is really great. It's in megavolt. So I think our initial condition is quite big current. So let me just reduce it to say 1 micro. Now let me see. Still it is in kilovolts. Earlier it was megavolt, it is now in kilovolt. This is the so for 1 milli 1 milli farad capacitor is actually a huge capacitor. We don't practically use such big capacitor. This is the kind of capacitor that you see in fan. If you have a ceiling fan, then you must have seen on the top of it, on the top of the motor there is a capacitor, okay, which is of the order of 1 milli farad capacitor, or 1000 microfarad we call it. Okay, so but the point is that you can give different initial conditions and then get some response out of it. Okay, it is not necessary that the circuit to give response you need to have voltage source or current source. You can have initial conditions, non-zero initial condition, and this is called zero input response. Okay, so is there any doubt from any of this experiment? I am stopping it here. So this will be your experiment number 5. It is called zero state input response. So that is what it is called, zero state input response. Zero state, okay, zero input response, zero input response. The other one is zero state response. So this is zero input response. The other one, earlier ones, experiment 3 and 4, they are zero state response, because we did not give any initial condition there. We only gave voltage source and current source and the response of the circuit to those. So that is zero state response. This is zero input response. The total response is sum of these. So that you can do. So whatever we have seen earlier, on the top of that, if you give a voltage source here, let's put in that also. So suppose, so let me go back to the voltage which I gave. So voltage on the capacitor or current in the inductor, or you can give both also. Voltage on the capacitor, that is B, I give it as 1 volt. Okay, so let me just run it and save it, and then I modify it. Yeah, so the 1 volt, it dies out. This we have seen. Now on the top of this, so let me also give one more initial conditions, that is dot IC current. There are two energy storing element, one is inductor, other is capacitor. So if I insist that the voltage on the capacitor is this and the current through the inductor is this, okay, so the current through the inductor, let me say it is equal to 1 milliampere. So two initial conditions. Voltage on the capacitor is 1 volt and current through the inductor is 1 milliampere. And then I would like to see what happens to the voltage. Okay, so this is the combined effect of both. Okay, so you see that this is a practical kind of voltage that you can get. So this is zero input response. Now the total response. to find the total response, what we need to do, we have to give an input also. So to give input, let me go to voltage source. Put a voltage source here, and then you can give various voltage sources. So let's go to advanced and give a pulse, something like a step. So initially it was 0, and then it goes to say 1 volt with a delay of say 5 micro, milli, 5 milli, because we are plotting for 30 milliseconds. So I am saying a delay of this, and then very quickly it goes, say 1 nanosecond. Very quickly it falls 1 nanosecond, and T1 is for 50 milli. Okay, so this is my input. Now we have two things. One is the zero's input response, and on the top of that I will have secondly zero state response, okay, which is entirely due to the input, and then I will add these two things. That will be my total response. So zero state response, zero input response, and finally I have the total response. Okay, these are some labels. It will not be executed. Just for our understanding, we are putting this. Okay. So now you see that two things are competing. One is the voltage source. So let me show the voltage source also. Okay. So voltage source is like this. It is remaining at 0, and it quickly goes to 1 at say 5 millisecond, and then it remains at 1 for the rest of the time. Now if you look at the output response till that time, it was entirely determined by the till 5 millisecond it was entirely determined by the zero input response. Okay, so zero input response is there. Then it was, what happened was that because of the step input, there is zero state response also coming into it, the picture, and then both are getting added up, and it is modified like this. So what we plotted in previous experiment, that is experiment number 4, and just before this what I plotted, they are getting added up, and the sum of these two is what is now we are seeing as the total response. Okay, so this part also you can include in this experiment. So you show zero state response and then the total response. Zero input response and the total response. Zero state response is already done earlier. Okay, so that's all. Any questions?